Hello all, I welcome you all to this session on basic thermodynamics. In this class, we are going to cover control volume and control surface, thermodynamic properties, extensive and intensive properties, state, path, cycle, thermodynamic equilibrium and quasi-static process. So first we will discuss on control volume and control surface. So we defined a thermodynamic system as a quantity of matter or region in space. If you consider a thermodynamic system as a quantity of matter, it is a fixed mass system. So mass is not going to cross the system boundary. It is quite similar to a closed system. On the other hand, if you have an open system where our attention is focused on a particular volume. For example, we defined the system as quantity of matter or region in space. For example, region in space in the sense, for example, if you consider to install an air conditioner for this room, we consider this region as our focus or our interest. So in that case, it is the volume upon which our attention is concentrated. So we call that as a control volume. So control volume is nothing but if you consider a system as an open system or a region in space, our attention will be focused on a particular volume and changes which happens to the properties within that volume is our interest. So that volume we call it as control volume, and of course this volume is bounded by number of surfaces which we call it as control surface. So this definition of control volume and surface comes into picture when you are considering a region in space or an open system where our attention is on a region in space. Okay. So next topic which we are going to cover is thermodynamic properties. What is a thermodynamic property, or simply sometimes we also call it as a property. So every system has a certain characteristics by which physical condition of the systems can be described. For example, it can be pressure, volume or temperature. Many more such properties are there. For example, if you consider an example of a cylinder and piston arrangement, what is its physical condition? You can say it as its pressure is. So you consider the gas inside that cylinder as a system. So what is its physical condition? It can be the pressure of the gas is this much, or the temperature, or the volume of the gas is this much. That itself is the thermodynamic properties, which describes what? Physical condition of the system. So again, if you look at the definition, every system has a certain characteristics by which its physical condition is described, that we call it as a thermodynamic properties. Sometimes we also try to say it as these thermodynamics properties are the characteristics which describe the state of the system. We have not defined the state of the system yet, but remember, it describes, the properties describes the state of the system. Later we will define the state of the system as well. So the simple examples are pressure, volume and temperature. Remember, these three are the most frequently used properties in thermodynamics. They are pressure, volume and temperature. So there can be two classifications in thermodynamic properties. One is extensive property. Extensive means extent. Extent means mass. So the properties which depends on the mass of the system, they are called as extensive properties. The properties which depends on mass of the system, we call it as extensive properties. For example, specific volume. The unit of specific volume is meter cube per kg. So it depends on mass, right? Per kg. So any specific property, specific enthalpy means kilojoule per kg. So it depends on the mass. So in that case we call it as extensive property. On the other hand, you have intensive property, the properties which are independent of the mass. So the properties which does not depend on the mass, we call it as intensive property. One good example of that is temperature. Now let us see the definition of state. So earlier we defined the definition of properties. The way we defined was, properties are the characteristics which defines the physical condition of the system, or in other words it is nothing but we are defining the state of the system only. So what is state? State is the condition of the system at any instant of time. Imagine a piston and a cylinder arrangement. So at any instant of time, the system which we are considering is gas. So it depends on the position of the piston. So that is the volume or pressure or temperature which you can measure, let us say. So now the state of the system is nothing but, if you define the pressure is this much, the temperature is this much, if you can measure the values, pressure, temperature, volume, that itself is the state of the system. So that is why when we were defining the properties, we said that properties are the characteristics which define or describe the state of the system or describe the physical condition of the system. So if you consider a pressure versus volume diagram, pressure versus volume diagram is nothing but, if you have a piston and cylinder arrangement, this is a state. What is this trying to tell you? At this state, the volume of the gas or the system is this much and the pressure is this much. So you have two values in a PV diagram or a pressure volume plot. Just imagine any XY plot. If you know the value of X and value of Y, you can notate it or denote it in a graph of two coordinates. So this is the state of the system. You know the values of pressure and volume. So this is at given instant of time. Let us say if you have a piston and cylinder arrangement, something like this. Okay, this is your system, the gas. Let us say if you can measure the pressure, pressure can be measured. If you install a pressure gauge here, you can measure pressure. Similarly, you can measure the volume. So if you can measure pressure and volume, let us say you get the value somewhere here, you mark this point, that itself is the physical condition of the system, or it is nothing but the state of the system. So state is nothing but a condition of the system at any given instant of time. So if piston moves to here by any operation, let us say the pressure is increased here, or volume is increased till here. So because of which you have a change of state. So what is change of state? Any operation in which one or more properties, it can be pressure or volume, properties of the system changes, then it is called as change of state. So if you can measure the pressure and volume at this state, that is state 2. So system has changed from state 1 to state 2. Okay, system has changed its state from state 1 to state 2. What properties have you have changed here? Both the pressure as well as the volume change. It can be only pressure can be changed or only volume can be changed. It depends upon the the way the change of state is happening. Similarly, you can go for the next definition, that is path. The succession of state passed through during a change of state. So this is what we are calling it as a path. Number of states can be there, intermediate states if you can plot, and the succession of states between the state 1 and state 2, we call it as path. If you define this, it is called as a path. Similarly, the process can be when the path is completely specified, the change of state is called as process. Now this can be denoted as process 1 to 2. This change of state, now you have defined the path, and this once this is completely specified, you call it as a process. This is how we try to denote process 1 to 2. One more definition is cycle. So, we generally say it as a thermodynamic cycle or a cycle. It is defined as series of state changes such that final and initial states are same or identical. For example, if the same example of this can be taken, let us say this is state 1 to state 2, change of state. Then if the system comes back to its initial state again by a process, you call it as a thermodynamic cycle. That is what we have defined, series of state changes such that final and initial both are same. Final and initial both states are at the same point, are identical, then you call it as a thermodynamic cycle. It need not to be just this much, it can be like 1 to 2, 2 to 3, then it can come back to its initial state. So, here it has process 1 to 2, process 2 to 3 and then process 3 to 1. But remember, series of state changes such that final and initial states both are same, are identical in this case. So, thermodynamic cycle is very important aspect in order to determine whether it, even in case of power producing or power absorbing cycles. Don't get confused with a mechanical cycle. Mechanical cycle is, if the piston is here, it goes to state 2 and comes back to initial state, it can follow a mechanical cycle. Mechanical cycle is the volume, just the it comes back to initial state. Whereas thermodynamic cycle means all the thermodynamic properties which were there initially, it should, when system comes back to its initial state or the final state, it has to attain all the thermodynamic properties as it was in the initial state. For example, pressure, volume, temperature, all of them should be same as that of the initial state. Then it is called as a thermodynamic cycle. Don't confuse with the mechanical cycle. Mechanical cycle means, if you consider an IC engine, in IC engine, piston during the suction stroke will be at the initial state. It goes on to the suction stroke, then compression, then power and exhaust. It has come back to its initial state in terms of mechanical cycle. Whereas the working fluid or the system which you had considered itself is not remaining within the boundary of the boundary of the system itself. So, in that case it is simply a mechanical cycle, whereas in case of a thermodynamic cycle, the system has to come back to its initial state. I mean to say, if you consider that the IC engine itself as your system, the working fluid which you had considered, if you measure the pressure, volume, temperature initially, then at the exhaust stroke, it has to come back to its initial pressure, volume and temperature, which does not happen in case of an IC engine, because at the exhaust stroke the exhaust valve will open and this the system itself will be let out of the system boundary. So, that is a simply mechanical cycle. The piston goes and comes back to its initial state. So, remember, thermodynamic cycle is the one where the properties, thermodynamic properties should come back to its initial state. Next concept which we are going to study is thermodynamic equilibrium. Now, if I have to tell a system attains a thermodynamic equilibrium, it has to satisfy these three equilibriums, that is mechanical equilibrium, chemical equilibrium and thermal equilibrium. If a system attains all these states or all these equilibrium, then I call that system is under thermodynamic equilibrium. Then what is a mechanical equilibrium? Mechanical equilibrium is if there is no unbalanced forces between system and surroundings or within the systems itself, then that condition we call it as a mechanical equilibrium. For example, if you consider a piston and cylinder arrangement, then if there is an unbalanced force between the system and the surroundings, for example, if there is a higher pressure here than that of the atmospheric pressure, let us say this is atmospheric pressure, if this is there, then what will happen? Piston starts expanding or piston starts moving to the right in this case until there is an equilibrium, until this pressure inside and the outside pressure comes to the equal state. So that case we call it as mechanical equilibrium. So if there is no unbalanced force within the system or between the system and surroundings, then that condition we call it as mechanical equilibrium. It is very important to have all these equilibrium conditions in order to say whether the system attains thermodynamic equilibrium or not. For example, if at all you want to describe the pressure, let us say any random value, let us say the pressure is 2 bar or 3 bar, it has to be at a equilibrium state. If it is continuously varying, you cannot say that at a given state pressure is 2 bar. It is quite similar to the the common example of speedometer, which will be in your automobile. If at all you want to say that the vehicle is going at 60 km per hour, the indicator what you see in the speedometer has to be there for a certain amount of time at least. If not, if it is continuously varying, you cannot say it the exact speed of it. Similarly, if at all you want to say equilibrium, the state of the system has to be at an equilibrium state or at rest. Okay. Similarly, you can define chemical equilibrium. The chemical equilibrium is defined as if there is no chemical reaction or mass transfer through diffusion within the system or between system and surroundings, then you tend to say that system attains chemical equilibrium. Thermal equilibrium, thermal means therm means heat or temperature. So if there is no temperature difference within the system, for example, if you take water and the temperature measured at any given point within the system has to be same. It cannot be like here it is 49 degrees Celsius and here it is 50 degrees centigrade. Then what will happen? The heat transfer will happen because of the temperature difference. So if at all you want to say the system is in thermal equilibrium, there should not be any temperature difference within the system or between the system and surroundings. For example, that is what happens. For example, this is at 50 degrees centigrade and the atmosphere, let us say it is at 30 degrees centigrade, then there is a chance of heat transfer. So now you may ask, can this be under thermal equilibrium? Yes, it can be, as long as the walls or the boundary is made strong. So that means to say you can attain any of this equilibrium by two ways. One is that you make the boundary so strong that there is no transfer of or there is no unbalanced force between system and surroundings, or there is no temperature difference. That is one way of attaining an equilibrium between the system and surroundings. The other way can be if the system is also having the same state as that of the surroundings, then also it will be under the equilibrium state. For example, in thermal equilibrium, if the temperature of the system is also 30 degrees centigrade and that of the outside or the surroundings is also of 30 degrees centigrade, then there is no question of there is unbalanced temperatures. So there is no heat transfer happening here. Then this can be under thermal equilibrium. So if a system attains mechanical, chemical and thermal equilibrium, then it is said to be a thermodynamic equilibrium. The next topic which we are going to discuss is quasi-static process, where quasi means almost, static means equilibrium. So we have learnt what is the importance of equilibrium, or we said thermodynamic equilibrium. So if at all you want to denote a point in a coordinate system, it has to be in equilibrium. That is what we said. If at all you want to say the speed of my bike is 60 km/h, it should not be varying continuously. The needle should be there at least at least statically at a 60 for some time at least, if at all you want to say the speed is 60 km/h. Similarly, if at all I want to denote or mark a point in a PV coordinate as state 1, at this point it has to be in equilibrium state. For example, let us consider a piston and cylinder arrangement. Let us assume that there is a gas which is considered to be our system. So gas is our system, and gas is under certain pressure and it has got certain volume and temperature. We call it as state 1. So the characteristic which describe the state of the system, we called it as properties. Very frequently encountered properties which we said it as pressure, volume and temperature. If you can measure pressure and volume, so remember it has to be equilibrium, means the pressure or volume should not be continuously changing, it has to be static. So we measured pressure P1, volume V1, we said it as state 1. So imagine there is a gas here and the piston, so and above the piston there is a weight. So assume that the gas, the pressure of the gas which is pushing the piston upward is equal to the weight of the piston. I mean to say this weight is balanced by the force exerted by the gas here. So there is an upward force here and weight is acting downwards. If it is under equilibrium condition, it has to be static. Okay. So that means to say the weight of the piston is exactly balanced by the pressure of the gas, or in other words you can say the force exerted by the pressure of the gas is equal to the weight which is acting downward. In that case it will be equilibrium, at equilibrium state, and you are able to measure the pressure, volume. So you called it as state 1. So there are stoppers here. So what we will do, we will remove the weight. So what will happen? Because of the unbalanced forces, if you remove the weight, the piston will move upwards till it hits the stopper. I repeat, if you remove the weight, suddenly the piston will move until the piston hits the stopper and stops, and of course it comes back to equilibrium at the this state. We called it as state 2. Once again you can measure the pressure, once again you can measure the volume, we called it as P2 and V2. State 1 is an equilibrium state, state 2 is an equilibrium state. So the piston is travelling from one state, one equilibrium state to the other equilibrium state. So you can mark the state 1 in your PV diagram, mark state 2 in your PV diagram, but whereas if you do not know the path through which the system moves from state 1 to state 2, the dotted line which has no meaning otherwise if you do not know the intermediate states or intermediate equilibrium states, you can say. So you do not know the process, you can also say that this is also the possibility, the other one is also possibility. How did the system moves from state 1 to state 2? It can be from this path or this path, which we do not know. Unless we know the intermediate states or in other words intermediate equilibrium states are measured or specified, you cannot define the path of the system. So this is of very importance because we need to define the path of the system. So how to make it, or how to make this process such that we can get the intermediate states as well. So let us divide this weight into very small number of equal sized parts. So we have divided this weight into number of small, infinitely small number of parts. So now if you start removing the weight one by one, what will happen? If you remove the weight one by one, I just remove the one weight, first weight, because of the unbalance in force, the piston will move a bit towards the top, and then it attains an equilibrium state. So you can measure that state, intermediate state. Now again you remove one more weight, you can measure the pressure and volume, that is of course equilibrium, it attains an equilibrium once there is no unbalanced force between. You remove one more weight. So similarly you can get the number of intermediate states between the state 1 and state 2. Then the path can be defined. That is when you call it as a path. So this can be defined only when you know the intermediate equilibrium points. So that is what we defined at earlier stage. Quasi-static means almost equilibrium. So this is like almost equilibrium process. This process which we call it as almost equilibrium, or in other words we also call this as reversible process. So why we call it as reversible process is because if you reverse this process, so that is from state 2 to state 1, system and surroundings both will come back to its initial state. Remember, if the quasi-static process is also called as reversible process because it has a characteristic. If you reverse the process from state 2 to state 1, both system and surroundings comes back to its initial state. Then only it is called as reversible process. And one more characteristic of quasi-static process is infinitely slowness, or infinitely slowness. Slow is the characteristic of quasi-static process. It is a very slow process. Remember, so from here onwards in any of the thermodynamic coordinate, if I write a process and draw a path, we are assuming that we know the intermediate states between the known states of state 1, 2 or 3 or 4, something like that. So we know intermediate state. So whatever the process we draw in any of the coordinates, if you are able to write a path, it means that we know the intermediate states, or in other words we are drawing a reversible process or a quasi-static process.